Hi everyone, this is Mrs. Musoff here. Today we're going to be talking about growth and decay, exponential growth and decay, but we're going to be talking about it specifically with the number e. Now you might be thinking, don't you mean letter? Well, no, e is actually a number in math. We call it the natural base, and that's because the base e shows up in a lot of natural occurring growths. All right, so the natural base e is approximately 2.718. It's kind of similar to pi in that it's a repeating number, right? It's irrational. It repeats. It has a lot of digits. There's no way to approximate it with a fraction, and that's what makes it irrational. All right, and the reason we would use base e is a way to describe something that is continuously growing. So for example, in the previous notes, when we talked about exponential growth and decay, we talked about like after a year it, grew 10%, or after a year it decayed 30%, right? We would use base E if we're talking about something that's constantly growing. So for example, one of the main methods of using E is like with bacteria, because bacteria is constantly growing. It doesn't just wait a year in order to grow. All right, so just so you can kind of see why we would want to use the base e instead of just a regular number. All right, it is called Euler's number. I know it looks like Euler's number, but it's pronounced Euler's number after the person who discovered it, and that was Euler. All right. So you're going to see a lot of, when we have a base e, it's really not too much different than the growth and exponential growth and decay that you've seen before. This is the equation if you have a base e. Just to remind you, right, the equation we learned before for normal exponential growth and decay was this. I'm writing it off to the side here. All right, it's a very similar equation to the one with the base e. The only difference is we kind of replace this piece in parentheses. That's what becomes e. And then in order to still account for some kind of rate, we put like an extra number here to represent our rate. So in this new equation with a base e, right there's base e, all right, there are only two numbers that you have to identify. This first number here, A, and then the second number is B. A is going to represent our initial value, just like it did in the last equation that we learned, right, the last formula. Okay, same A. And then B is going to represent our continuous growth or decay rate. Now I want to kind of clarify something here because in yesterday's notes, R represented the growth rate, and that was actually the percentage. So if it was growing by 10%, right, we used 0.10 for R. Here, this B value is called the continuous growth rate, which is different from the percentage. So if I told you something was growing by 20%, that wouldn't be the continuous growth rate. 20% would be how much it grows after a year, but the continuous growth rate is how much it's growing constantly. All right, so it's just kind of a slight nuance that makes it a little different than the R value before. Now, it doesn't come up much. We can still kind of refer to it as the growth rate or the decay rate, but next year you'll see how kind of that value is a little different. All right, in this equation, the way you can tell if you're dealing with growth or decay, because in the last equation you could tell if you're doing plus or minus, but here we don't have that. So growth is if B is positive, all right, greater than 0, that means if it's positive. So for example, if I had an equation that looked something like this, all right, that's just kind of an example. Because B is 0.5, and that's greater than 0, I know that that's growth. All right, it's decay if that B value is less than 0, meaning it's negative. Which makes sense, right? Growing, positive, decay, negative, seems reasonable. All right, so again, to give you another example, if I had something like this, 5e to the negative 0.2x, right? Because that's a negative 0.2, and that's less than 0, that we would say is decay. Okay, so let's try a couple more examples like that just to make sure that makes sense. As always, if you haven't gotten the hang of this yet, anytime we're doing these videos with handwritten notes, I encourage you to pause so you can write down the problem on your own. And that way, as we go through it, you're not scrambling to scribble down all these words and then not really paying attention to the problem. All right, so feel free to pause, write it down, and then play again when we go through it. So example 1, it says, determine if the following equations represent growth or decay. Then identify the initial value and the continuous growth rate. So we're asking you to do 3 things here. Does it represent growth or decay? That's number 1. Identify the initial value, number 2. And identify the continuous growth rate, number 3. Okay, so first things first, is it growth or decay? And I guess this should say growth or decay rate, right, depending on the problem. All right, so in this first one, y equals 3e to the 0.05x. The first thing I want to know is, am I dealing with growth or decay? And that's going to be based on our b value. All right, so here b is 0.05. Since 0.05 is greater than 0, right, it's positive, that should tell you that we're dealing with growth. All right, so this represents exponential growth. So that's answer number 1. And then the next things it asks us for is to identify the initial value and the continuous growth or decay rate. Well, the initial value is this first number here, that's a. All right, so I have a equals 3. That means my initial value is going to be 3. And since there are no units here, I don't really know 3 what, so I'm just going to say 3. Okay, and then the last thing they're asking us for is the continuous growth rate. And that is our b value, which we already identified before. B is 0.05. So what that means is that's how much this function is growing constantly, not necessarily like how much it's growing after a specific time interval, right? Like after a year. Okay, but then that's it. That's all we're trying to do. All right, same thing in letter B. So y equals 200e to the negative 0.13x. Again, first things first, is it growth or decay? That's going to be based on that number here, b. Since b is negative 0.13 and negative 0.13 is less than 0 or negative, that tells us that we're dealing with exponential decay. All right, the next thing is to find the initial value. The initial value is the number, it's always that number in front of the base. All right, so whether you're using a base e or any other base, that a value, the number in front, is always your initial. And so here my initial value is going to be 200. And then in this case, this would be the continuous decay rate. That's the b value we found earlier, which would be negative 0.13. Okay, and that's it. All right, one more example. All right, so example 2, again, feel free to pause to write it down. We're starting to talk about exponential growth and decay, and coincidentally, that's the exact same thing that this coronavirus, COVID-19, is dealing with, right? Exponential growth and decay. If anyone's been reading up on it, I'm sure you've seen that word in a lot of the notes, because that's how this virus ends up kind of spreading, right? One person that's infected infects multiple people and so on and so forth, and that exponential growth can really get out of hand. And that's kind of what we're going to be talking a little bit about in these days notes. So I figured, why not bring it to this example? We can kind of analyze it a little more and talk about it. All right, so it says, between April 4th and April 15th, the number of confirmed COVID-19 cases can be shown by A equals 277,965 e to the 0.071d, where A is the number of confirmed cases after D days. And this is just data that I pulled from Our World in Data by the University of Oxford. They've just been collecting data from all countries about confirmed cases and things like that. So feel free to take a look at it online if you want to see these numbers. All right, so part A says what was the initial number of cases on April 4th? Well, remember what we just talked about. The initial value is always the number, in front of E. Ooh, sorry about that. Jumped. Okay, so here that number in front of E is 277,965. And I am going to try and use units here since now we're talking, with context. So the initial number of cases, I would say 277,965 cases. Okay, so the initial shouldn't require too much work if it's in the form we're familiar with. Okay, this next problem, which should say letter B, all right, it says how many cases will there be after 30 days? Well, the nice thing about some of these problems is if you're given the equation, then really it just becomes kind of substitution, right? How many cases will there be after 30 days? Well, how many cases is asking us to find A, because that's what A represents, the number of confirmed cases. And then after 30 days, that's telling us this other variable D. It's saying D is going to equal 30. So what I'm going to do is take the equation that they gave me and just plug in 30 for D. So it would become 277,965 times e to the 0.071, and then instead of D times 30. All right, now we would use our calculator for this, so I'm going to turn over to my calculator, and I'm going to type it in. 277,965. Did I do that right? 277, good. And then the E, the base E button, if you take a look on your calculator where it says log, if you look at the button right below it, that actually says ln, and right above it in blue is e to the x. So I'm going to press second and then the ln button, and that's how I can get my base e to show up. All right, it's 0.071 times 30. And remember, some of our calculators, you might need this to be in parentheses. So in fact, I'll go ahead and put it in parentheses for you, just in case you aren't getting the same numbers as me. You can kind of go back and make sure we've got parentheses. All right, and so after 30 days, let's see, 3, so that'd be 2,339,038 cases. Typically when it's, you can't have a decimal of a case, so I would round down. So 2,339,038 cases. All right, so let's write that down. 2,330,000, I've already forgotten, 9,038. And again, I like to have units, so that's, cases or confirmed cases. The reason we're specifying confirmed is, right, supposedly there are a lot more cases than they can confirm. So, this is just confirmed cases. Okay. And just something else to kind of note. So this says after 30 days we'll have upwards of 2 million confirmed cases. But do you think that's really what's going to happen? Right? Ideally, with all the work that we've been putting in order to flatten the curve, these numbers shouldn't actually be what's happening after 30 days. And that's why I say this equation is only valid currently, right, between April 4th and April 15th. Ideally, we're taking measures to adjust this curve so that it will no longer be exponential growth. All right, that's the goal at least. All right, so there's a silver lining there that we're headed for, not all doom and gloom. Okay. All right, well, thanks for tuning in. If you have questions, make sure you write them down, email your teacher. Otherwise, thanks again.